right? I thought there'd be data. Is anyone out there?
Hello and welcome back. All right, so we are going to talk about GLERTs, but I have one more thing to say about the UMP test, which is now on the homework for you to derive a test. And the only thing I really want to say is that I need to define a term that I've used in problem 2 on the homework, and that is a monotone likelihood ratio family. So before I do that, let me just say that so far we have not seen a UMP test for a composite null hypothesis like this, theta less than or equal to theta naught versus the alternative, theta is greater than theta naught. We have only worked with simple, so this is our first composite here for a UMP, a uniformly most powerful test. And so the way we've worked this in the past is, again, in the past, we only had like theta equals a theta naught versus some kind of alternative, like, for example, theta greater than theta naught. And we translated that into two simple hypotheses, theta equals theta naught versus theta equals theta 1 for some fixed theta 1 greater than theta naught. And then we used the Neyman-Pearson lemma to find a best or most powerful test for this simple versus simple. And then we hopefully were able to show that the simple test that we came up with did not depend on the particular value of theta 1 that we chose. So hopefully test doesn't depend on the particular theta 1. I regret now making this a marginal note. It's going way on. The particular theta 1 chosen, this would imply that the Neyman-Pearson test, I've never called it that before, but the test resulting from the Neyman-Pearson lemma is uniformly most powerful for the simple versus composite. And so that's what we've had so far. And so now for the first time, going back up to the upper left, I want to talk about some particular forms of this particular form of a composite null hypothesis, or the reverse. So I could have theta greater than or equal to theta naught versus theta less than theta naught. So I've already hinted to you that if you just do the Neyman-Pearson thing, which is create the likelihood ratio. So we call this lambda of x and theta naught and theta 1 in the simple versus simple case. And this was the joint PDF with theta naught plugged in over the joint PDF with theta 1 plugged in. Now, you know that Neyman-Pearson tells us to reject the null hypothesis if this is less than or equal to some k, and k is determined to give us a size alpha test. And so this is what you're going to show on the homework. So if we reject if this lambda is less than or equal to k, I'm trying to say very clumsily that if you're given a composite null hypothesis like this, in some cases you can just treat this as equality. In some cases. And that is going to be whenever the the way you define alpha as a maximum over all of these values when the maximum occurs at the boundary. So let me try to write that, where K is such that alpha is the probability that this guy is less than or equal to K when the parameter is theta naught. So no max here, even though the null hypothesis is composite. And this test works in certain conditions sometimes. And so let me just write out what I'm trying to say. I'm trying to say again that if the maximization over the thetas in the null hypothesis occurs at the boundary, then you can use our old test. And in order to show this, I want to define a monotone likelihood ratio family of distributions. So I didn't say that very well, but here's a definition that you need for problem 2 on the homework. So the model or distribution represented by a joint PDF, f of x and theta, is called a monotone likelihood ratio in a statistic T if. So before defining this, whenever you see this drives me nuts, but you know, monotone means monotone increasing or monotone decreasing, and it doesn't have to be strict. I'm not saying strictly monotone. Whenever you see this definition in statistics, the default is it means increasing. Well, actually, it means non-decreasing. And it drives me crazy that people will talk about having a monotone likelihood ratio and try to apply a test without really thinking about, it just drives me crazy that we don't specifically say that here. So monotone in this definition defaults to non-decreasing, but we could define a non-increasing monotone likelihood ratio. Okay, so the definition is two things. So one is that the joint PDF at theta naught and the joint PDF at some theta 1. And although these thetas look like they're coming from a null and alternate hypothesis, they're not. It's just two values of theta. So maybe I should have called them theta 1. Let's do that. I'm going to call them theta 1 and theta 2. So these are distinct or not equal whenever theta 1 is not equal to theta 2. This is not the interesting part of the definition. This is just sort of a technicality. Whenever theta 1 is not equal to theta 2. And the important thing is that the likelihood ratio which we get from our lambda of x and theta 1, theta 2. Again, there's no hypotheses in this definition, which is why I'm not using a theta naught and a theta 1. So it's defined the same way. And we want this to be a monotone non-decreasing. So all the kind of negatives and double negatives are confusing, maybe. So I'm going to say monotone increasing, but not strictly. So it's increasing, but can be flat. So that's what I mean by non-decreasing. So this likelihood is a non-decreasing function of the function that defines the statistic. So non-decreasing function of this little t of x whenever theta 1 is less than theta 2. All right, that's just a definition. And you can imagine changing the yellow thing in the upper right corner to non-increasing, and then you would just have to change this. But again, when people don't specify, they mean non-decreasing. And the point is that if your family, your distribution family comes from a or if you have a distribution and a statistic that is so that your distribution is a monotone likelihood ratio family in the statistic T, then this just this looks horrible, but this just kind of simplifies to basically here's the result that you're going to show. The lambda, the likelihood ratio that you would consider in a hypothesis test, this is going to be less than or equal to k. This is going to happen if and only if. So I'm claiming that if this is an quote unquote increasing function of t, then this is going to be equivalent to saying that t of x is less than or equal to some k1. Right? Because if the thing I circled is increasing, like this is some, I don't know what to use. I'm going to say maybe G, but it looks a lot like our sufficient statistic thing. So if this is some function of a statistic, then if as this T of X increases, the entire G increases, then talking about the G being less than or equal to some K is equivalent to talking about the T being less than or equal to some K1. Does that make any sense? It's, it's what you would kind of think, right? You start your hypothesis test by writing something like this down, and then you solve for the X's, and that becomes a statistic, say the sum of the X's. And assuming this ratio was monotone, non-decreasing in a statistic, then that circle being less than or equal to K is equivalent to the statistic being less than or equal to some other K. Okay, so problem 2 in the homework, you are proving, you're given a test and you want to prove that it is uniformly most powerful for this composite versus composite. And you are also given that you have a family of distributions and a statistic that such that you have a monotone likelihood ratio in that statistic. It'll be so much easier once you get into it. So kind of don't want to say questions, but I don't know, questions? It all made it look really hard, but it's just this. It's just saying if your lambda is less than or equal to k, then you can reduce this. This is me dots, reduce this down to a statistic less than or equal to something else. And so you can imagine, right, if it's if that G is monotone decreasing in the statistic T, then this big circle saying less than or equal to k would be equivalent to the statistic being greater than or equal to some k1. Okay, let's talk after you've had a chance to digest the problem. Okay, so what is new? GLERTs. GLERTs are new. So I love GLERTs. I love saying GLERT. GLERT stands for Generalized Likelihood Ratio Test. They are good if the UMP doesn't exist or if the UMP is too hard to find. Then I've said it a few times now, this is the MLE to the UMVU. This is to the UMP test as the MLE is to the UMVU. UMVU is best, but hard to find, doesn't always exist. And in real life, you're probably going to use a GLERT. In real life, you're probably going to estimate with an MLE. Okay, so to define a generalized likelihood ratio test, I need to define a generalized likelihood ratio. And so here goes. Suppose I have x1 through xn with some joint PDF f of the vector x and theta. So I'm going to define the so-called generalized likelihood ratio. I'm going to call it lambda, just like before, but it's not going to be well, it has to do with the hypothesis test. So I really should have started this by writing down, we're doing kind of general hypothesis testing. So theta is in some subset of the parameter space, this capital theta naught, versus the alternative that theta is in the rest of the parameter space, taking away theta naught. So that's just the complement of theta naught and theta. The generalized likelihood ratio is, we're going to denote it by a lambda of x. It's not going to depend on a theta naught and a theta 1 because there is no theta naught and theta 1 here. There's an entire set, capital theta naught, but there's no fixed theta naught and theta 1 here. So here's where we get really general. The UMP tests are really hard if they exist when we stop talking about less than, greater than, not equals. We want to do the really crazy tests, like the null hypothesis is that theta is in this bizarre union of disjoint sets or something like that. So this is defined to be the likelihood function evaluated at something I'm going to call theta naught hat, which I'm about to define, over the likelihood function evaluated at some theta hat. And here, L of theta is the likelihood function. Theta hat is the maximum likelihood estimator for theta. And theta naught hat is the so-called restricted MLE. And this is the MLE restricted to, we're going to maximize the likelihood, restricted only to the set of thetas where the null hypothesis is true. So, okay, so we're going to maximize L of theta over all theta in the kind of null hypothesis set. So this is the basis for the generalized likelihood ratio test, and the generalized, I guess I have to write this one more time, likelihood. So yeah, this is a second definition, I guess. The generalized likelihood ratio test, or GLERT, says to reject the null hypothesis in favor of the alternative whenever this thing is small. So I think I might be predicting what's on some of your minds right now. Let me finish writing this, and then let me bring up what I think some of you might be thinking. So reject in favor of the alternative if lambda of capital X is less than or equal to K, where K is chosen to give a size alpha test, i.e., you get alpha by maxing or suping, supremums, if the max doesn't exist, theta over the null hypothesis set of parameters, the probability that lambda of capital X, because it's a probability, is less than or equal to K when the parameter is theta. That's just what it means to be size alpha for this composite null hypothesis. So a couple of words about why this is a test. So something I think some of you might be thinking is, I'm going to scroll up. Sorry. And look at the GLER, the generalized likelihood ratio. You'll notice that I have the likelihood and I use the MLE restricted to the set of parameters in the null hypothesis. And down here, I use the MLE not restricted at all. And I think you might want to use in your denominator the MLE restricted to when the alternate hypothesis is true. I think that's a very natural extension from what we've already done with the simple versus simple, where we looked at the likelihood at theta naught over the likelihood at theta 1. So I think, again, it's totally natural to want to put here the MLE restricted to when the alternate hypothesis is true. And you absolutely can do this because this is a test. It's not a best test. It's kind of like an estimator. You know, as long as it has size alpha, you have made a test of size alpha. But the reason I didn't use and no one uses, well, not many people use the MLE restricted to when the alternate is true, is because the beauty of this test is when trying to figure out the cutoff K and this probability, this can get really hard, but I have kind of an asymptotic result for the distribution of this thing under some pretty minor assumptions. So yes, I mean the full MLE. And yes, it could have been the MLE restricted to the alternate hypothesis, but it's just a test, not a best test. We can use whatever we want as long as it has size alpha, and using this makes something coming up much more convenient. Okay, any questions? It makes a lot of sense though, I think, right? This is, especially if you've got discrete random variables when the likelihood is the joint PDF, which is like probability. So this is kind of the maximum. I don't know if you could see that arrow, get a laser pointer. Right, this is the likelihood rather than evaluating at a single point. We're evaluating it at its maximum, and then we're evaluating the likelihood at its overall maximum, and this is the restricted one. And so if the overall maximum height is much larger than the maximum of the likelihood when restricted to the null hypothesis, it seems like the null hypothesis maybe shouldn't be true. So you're going to reject when this is small. All right, so let's just find some GLERs and worry about the GLERT later, because the finding K is the same as it's always been. You then set up your alpha equation and you try to find it. So here are some GLR examples. The first one, suppose I have x1 through xn, IID normal with some mean mu, some variance sigma squared, and sigma squared known. I will take that assumption out in a few minutes. So find the generalized likelihood ratio for testing the null hypothesis that mu equals some mu naught versus, I know I said we get crazy with the parameter space. We're not quite there yet. Mu not equal to mu naught. So you would need a GLER to do a GLERT, and you probably want to do a GLERT in this case because we showed in this case that a UMP test does not exist. Because if you try to do the UMP, you fix a mu1 in here, and you'll get a test based on X bar, but it will have the inequality going one direction versus the other direction, depending on where you chose your mu1. So we saw that this does not exist as a UMP test. So we're going to try GLERT, but right now just the GLER. Okay, so the regular or unrestricted, not U-restricted, unrestricted MLE here is just X bar. So I'm just going to call this mu hat, and it is X bar, just the normal MLE. And the restricted MLE, so we're calling this mu naught hat. In this case, it's super easy. We are looking at some kind of likelihood function. It's not necessarily normal looking, but it does have one unique maximum. So that's not supposed to be a normal curve. This is supposed to be the likelihood function. And so here is the unrestricted MLE. And then the restricted MLE, we're not going to look at all of these mu's. We're just going to look at restricting to this set. So it's just this single point. So the unrestricted MLE is just the point, right? Because we're maximizing over a single point. Does that make sense? So let me just write that. We maximized L of mu over the set of mu's such that mu equals mu naught. I mean, there's only one value there. It's the max, it's the min, it's everything. Okay, so then we've got our, right, a likelihood here is proportional to the joint PDF. Because sigma squared is known in this problem, I can drop the 2 pi sigma squared to the minus n over 2, and a likelihood is e to the minus 1 over 2 sigma squared, sum of the xi minus mu squared. And so the generalized likelihood ratio is we're going to take L of the restricted MLE over L of the actual MLE, and this is L of the point mu naught over L of. So right now I'm using lowercase letters. Once I get into probability, uppercase letters, or maybe all uppercase letters now, but I am going to write X bar. So just so you know, that's not a vector. That's the sample mean of my n little x's. So looks a lot like a vector. Okay, so if you plug this stuff into this, you end up with e minus 1 over 2 sigma squared, the sum of the xi minus mu naught squared minus the sum of the xi minus x bar squared.
Question?
Yeah.
Okay, so I just want to understand why. So is X bar special in any way, or could we choose any estimator of mu?
It is, yeah, it is special in that we need to, for the generalized likelihood ratio test, mu hat is the maximum likelihood estimator for mu. So if you have a normal distribution with known variance, and so you just have that one parameter mu, and you just decided to find the MLE, you would get X bar. Okay, I said we weren't going to do tests now, just the GLR, but I guess I'll stick to it, but I would set this less than or equal to some k and kind of solve down for the x's and then find the K1, K2, or K5, or whatever you called it, to make this test have size alpha. And we'll do this example, but let me get through some more GLRs. Okay, all right, so did I put a number on this? Yes, my second GLR example. Suppose I have x1 through xn. So again, I'm not really concerning myself with the tests right now, just the setup for the test. The normal mu sigma squared, and still sigma squared known. And I want to find the generalized likelihood ratio for testing. So I want to move up to a composite null hypothesis. Let's say mu less than or equal to mu naught versus mu greater than mu naught. Yeah, that'll work. Okay, so we need to find, well, we need the likelihood, which I've already written down. Let me go back and cut and paste that. Okay, so here's our likelihood. And so the unrestricted MLE is just the MLE here. And if you tried to maximize this with respect to mu, you would get X bar. So if it's an estimator, it is random and capital. And so the restricted MLE here is a little trickier than it was before. So under some mild assumptions, those of the Cramér-Rao lower bound, those kind of regularity conditions, our MLE exists and is unique. And so if you imagine a picture of the likelihood function, then there's only one maximum. I'm not even saying that likelihood looks like that. I'm just trying to say it's one maximum and it's not necessarily a nice symmetric normal distribution, although kind of is. So in this case, if this is my likelihood function and this is where the maximum is, that is the MLE mu hat. And then it totally depends on where mu hat is relative to the fixed value of mu zero. The fixed value of mu zero lives on this graph somewhere. Maybe next time you sample this, your mu zero is in the exact same place, but the peak has moved. You know, mu zero is mu zero, it's just fixed. Sorry about all the scrolling. But the max is moving around. So it's sometimes on one side of mu zero, sometimes on the other side. Okay, so the restricted MLE, we want the MLE restricted to, in this problem, the region where mu is less than or equal to mu zero, restricted to the null hypothesis set. And that is over here. And in the next picture, it is over here. So it is, the restricted MLE is actually equal to X bar if X bar is less than or equal to mu zero, which is what's going on in this first picture. And I also am kind of banking on the fact that we kind of know, at least we've claimed, that the MLE exists and is unique. So it's we have to be increasing on one side of it and decreasing on the other side of it. Okay, so to finish the restricted MLE off, I'll put a bracket here. It's actually mu zero if X bar is greater than mu zero, because in this case, if you're looking at the orange stuff over here, the maximum over this region occurs right at that endpoint. Okay, so the generalized likelihood ratio, not test, but generalized likelihood ratio is lambda of, I'm going to just stick with capital letters, lambda of X, which is the likelihood at the restricted MLE divided by the likelihood at the unrestricted MLE. And this is, in the case that X bar is less than mu zero, so in this case, the restricted MLE is just X bar. So I get L of X bar over L of X bar if X bar is less than or equal to mu zero. In other words, I get 1. And then I get whatever it is I get over here, I guess E minus 1 over 2 sigma squared, the sum of xi minus mu zero squared minus the sum of xi minus x bar squared if x bar is greater than mu naught. Now these things, they coincide at the equality, so it really doesn't matter where I put the equals in terms of my less than or equal, greater than or equal. So yeah, 1, I don't want to rewrite this whole thing. So 1 and that thing. So I'm just finding some GLERs today, but finding the GLERT is going to be, we're going to do it in this problem, but it's extra tricky, right? Because the GLERT, the test is going to be to reject the null hypothesis in favor of the alternative if this lambda is less than or equal to some k, where k is such that the maximum over all mu less than or equal to mu naught of the probability of rejection meaning this lambda is less than or equal to k when the parameter is mu, this has to equal alpha. And so to solve for k, we need to be able to write down this probability. And so to do that, I need to figure out what lambda is, and it depends on whether or not x bar is less than or equal to mu naught or greater than mu naught. So we would have to do this by conditioning on the value of x bar. And so I'm going to have some conditional probabilities here, which is going to be confusing with that semicolon, I think. So I'm just going to change this notation and write P sub mu to mean the same thing. The probability that lambda of the sample is less than or equal to k when the parameter is mu. So I'm just moving this out because this is going to be the probability when mu is the parameter that lambda of the vector x is less than or equal to k, given that x bar is less than or equal to mu naught times the probability. I don't know if you guys haven't seen conditional probabilities that much. Like if you came from Markov, you definitely know what I'm going to write here. So I'll just write it differently first. So this is and x bar is less than or equal to mu naught, or add the disjoint event probability that lambda of x is less than or equal to k and x bar is greater than mu naught. Maybe you want to solve it this way, or maybe you can write this as the probability under the assumption that mu is the parameter, lambda of x less than or equal to k, given x bar is less than or equal to mu naught, over the probability that x bar is less than or equal to mu naught under the mu assumption. And it's a lot of work. We'll do it, but today is just GLERS. So finding the actual test, meaning finding the k that gives you the right size, is hard because this is a very clean example. It's a normal distribution and the null hypothesis is not some wild set. It's just a simple less than or equal to. And yet this is a lot of work. And so even in this case, you might want to use the asymptotic result I've alluded to, which is we're going to know the distribution of this lambda for large samples in some cases. Okay, one more GLER. So this is my third example. So x1 through xn, IID normal, mu sigma squared, and both mu and sigma squared are unknown. And suppose we only want a test involving the mean. So I'm going to do the same exact setup. The mu is less than or equal to some mu naught versus the alternative that mu is greater than mu naught. I don't know sigma squared, but I don't even care about a test involving sigma squared. So, you know what? That's going to be super ugly. I'm going to make this a little simpler. I'm going to change my null hypothesis to an equal sign, so we don't have to deal with two unknowns and that craziness that went on in the last example. Okay, so the generalized likelihood ratio is going to be the likelihood. Now, the likelihood now depends on both mu and sigma squared because that's no longer a constant that can be ignored. So we're going to have to plug in the restricted MLEs over plugging in the actual MLEs. So this sigma naught squared hat is a restricted maximum likelihood estimator for sigma squared under the assumption that the null hypothesis is true, even though it wasn't in the test. And so the regular unrestricted MLEs, you know, the mu hat is going to be x bar, and the sigma squared hat is almost the sample variance, but it's the biased version. It's the sum of xi minus x bar squared over n. And restricted, the mu 0 hat, we are restricted to the case where mu can only be mu 0. So this is just, again, maximizing a likelihood over a single point. And then the sigma squared naught hat is going to be you maximizing the likelihood with your restricted MLE plugged in. So you've got a likelihood that looks like this: sigma squared to the minus n over 2. Yeah, the 2 pi if you chose to keep it. Sum of the xi minus mu. And when we found the MLEs, we took the derivative with respect to mu, and we took the derivative with respect to sigma squared. And from the first equation, we found out what mu hat was, and then we plugged it into the second equation. And if you did that here, you're just going to end up with the MLE looking the same as before, but you're not using x bar, you're actually using mu naught. So that means you're maximizing this with respect to sigma squared, but you're restricting this to be mu naught. And so the restricted MLE is going to be the sum of the xi minus mu naught squared over n. So again, that's going to be what you get if you try to maximize the circled likelihood over sigma squared, but you have mu pinned down to be mu naught. So the first example, we can find k pretty easily. The second example is a lot more work with those conditional probabilities. And something I want to prove to you next time is a famous theorem known as Wilks's theorem. And I'll give you all the conditions next time. There's actually 6 of them. They're regularity type conditions. So under conditions, -2 times the log of the likelihood ratio converges in distribution to a chi-squared with some number of degrees of freedom that's determined by the setup of the hypotheses. And so I'm running out of time to finish this off. Whenever you're trying to solve for a k, usually we simplify this. We kind of get down to a sufficient statistic, which we isolate the x's. But we could actually make things more complicated by taking the log on both sides and -2 on both sides. So this is going to be p -2 log likelihood greater than or equal to -2 log k. And then we can treat this as approximately chi-squared for a large sample size. And so then I would just give this a name like W, and I would try to find the actual k that gives me the right size of the test using a chi-squared table. So that's, I think, the true power of these tests, because they get really hard really fast, but everything is chi-squared. Next time on mathematical statistics. Sorry, I went over.